All right, let's prove Theorem 72 here. So again, this is an optional video. You can just read it instead if you want. But I do sort of like going through some of the important theorems. So if it's an implication overall. If f is a function, then we have this if and only if statement as a conclusion. So we start by assuming f is a function. So we've assumed f is a set of pairs with that for all x, y, z condition. And then I need to prove this if and only if. So the proof splits into two parts, like this. So first part, assume f reverse is a function. And for this, I'm allowed to call it f inverse because it is a function. So it is the inverse of f. So assume f inverse exists. That's another way people put it sometimes. But it's just saying f reverse is a function. Then I need to prove f is injective. So let's see, there are a couple of ways of proving a function is injective. I could, let's see, injective. I could use the definition and be like, okay, consider any x, y in the domain of f, and then assume f of x equals f of y, and then I try to prove that x equals y. That's one approach. Or I could use Theorem 58 and do this thing with pairs. Now, typically, I would recommend this approach. In almost all cases, I would recommend this approach. But here, it actually makes, this is the one case where it makes sense to use this thing in terms of pairs, because we're going to relate it to this thing, the definition of function up here. Okay, so I'm going to show f is injective by showing this. So let me write down what I'm going to show. So we will prove that, let's see, for all x, y, z, if the pairs x, y, and zy are elements of f, I'm trying to prove f is injective. So if I have two pairs in f with the same output position, then the input positions must be the same, x equals z. So I'm proving this universal, so I'll do universal generalization. Consider any situation where you have this holding. Now, can I prove that x equals z? Well, what do I know? I know that f reverse is a function, right? And I have essence of reversal, that very convenient way of using reverse is just pairs being in a set is the same as the flipped around pairs being in the reverse. So by Theorem 67, essence of reversal, yx, yz are in f reverse. So I just flipped the pairs and then slapped on a reverse symbol. Now, I know f reverse is a function. That's why I flipped these around, because I want to use that fact. And here's two pairs in f reverse with the same first position. Since f reverse is a function, the second positions must match. So we must have x equals z. And that's it, right? Yes, we needed to prove this, we need to prove x equals z, and we did. Okay, now for the other direction, assume f is injective. Now I'm going to try to prove that f reverse is a function. So to do that, consider any situation where you have two pairs, x, y, x, z, in f reverse, and then we'll try to show that y equals z. That's how you show something as a function, right? I guess we also have to say f reverse is a set of pairs. Yeah, maybe I should say that. Then f reverse is a set of pairs. We can just say by definition 66. It's defined to be a set. A reverse of a set is always a set of pairs. Okay, and then the remaining condition to check is that whenever these two pairs are in there, it follows that y equals z. So can we prove that? Well, again, the theorem 67 makes it very simple to work with these reverse things. So just the flipped around version of these is in there. And now let's see. So since I'm assuming f is injective, right? And I know that an injective function satisfies this property, right? This is an if and only if. So I can use theorem 58 to conclude that, anytime I have two pairs with the same second position being elements of f, the first positions must be equal. So here's two pairs with the same second position, both are x, so therefore y equals z. So by theorem 58, right? It is theorem, yeah. By theorem 58, since f is injective, y equals z. And that's all that's needed to prove that f reverse is a function, right? So that's it. Now I notice something a little bit weird here. It looks like I referenced theorem 58 in this half of the proof, but I never mentioned theorem 58 up here. So I think the issue is that I said we will prove this, but I never said why that is sufficient to prove that. So that is a little weird. I should probably reference theorem 58 in both halves if I'm using it in both halves. So how about I do this? By theorem 58, we need to prove that this, and then that's what we did. So it was because of theorem 58 that proving this proved what we actually wanted, which was that f is injective. So you see this is using the fact that theorem 58 is an if and only if. We used one direction of theorem 58 and then another direction of theorem 58. Now, it's kind of tempting to think that if you have f injective from x to y, that since f reverse is now a function, that it would map y to x, right? It's tempting to think that because you're just flipping the arrow around. But be careful, because the mapping notation is sort of not symmetric in how it treats x versus y. The mapping notation says that x is equal to the domain of f, but it only says that y contains the range of f. So because of that issue, you will find that we cannot have, it's not necessarily true that y fits here. So when you flip things around, you might have something different here. Okay, so what I'm describing is captured here in this theorem. If f maps x to y and f is injective, then you cannot know that f reverse maps y to x, but you know at least it maps the range of f, whatever that is, to x. So the range of f might not be y. But if the range of f is y, in other words, if f is surjective, then you can put a y here. So if f is injective, then reversing gives you a function. If it's also surjective, then the range of f is y, and that's what ends up going here. So if you have, in other words, a bijection, something that's both an injection and a surjection, then you have this very nice situation where if it maps one way, then the reverse is also known as the inverse, maps the other way. All right, so I think I'm going to make this one of the presentation problems. Let's do a week of easier presentation problems for this time around. I think I made the ones last week a little bit challenging.